Okay, so I guess I'll start now. Maybe it looked like I started a while ago, but so this is the second part of my lecture from yesterday, and let me just start by recalling what we did yesterday, also in Jan's lecture. So one of the main things we proved is something I'm going to call theorem A, which is a statement about expected characteristic polynomials of certain random matrices. The random matrices were sums of independent rank 1 random matrices. So you have m independent random vectors R1 through Rm. Then the theorem, we proved two things. One is that the expected characteristic polynomial is real rooted. So RR means real rooted. And in fact, we said, well, we derived a formula for it, and we said, actually, this expected characteristic polynomial only depends on the covariance matrices of the random vectors. So these AIs are the covariance matrices of the random vectors. And this is something that we defined as a mixed characteristic polynomial. So the first part of the theorem was that these expected characteristic polynomials are real rooted. The second part of the theorem, which was proved by Jan, essentially, is that once you have this real rootedness statement, it allows you to compare the roots of this expected characteristic polynomial to eigenvalues of the random matrix. In other words, roots of the individual polynomials. And in particular, we have that for such a random matrix, the largest eigenvalue is at most the largest root of the expected characteristic polynomial with non-zero probability. Okay, so not with high probability or anything like that, but with some probability that's greater than 0. And Jan showed how, part 1, this real rootedness statement, implies part 2 via this interlacing, this inductive interlacing, common interlacing argument. Okay, so that's a summary of the main thing that was proved yesterday. And one of maybe the main application was to show existence of Ramanujan graphs, which required an additional ingredient of bounding the roots of these polynomials. So what I'm going to do today is prove one theorem, which I'm going to call theorem B, which is a more quantitative statement than what's shown here. So here we showed that these polynomials have real roots. Theorem B will give us a bound on the roots of these polynomials. So here is theorem B. So if we have m positive semi-definite matrices, which add up to the identity, and have trace bounded by epsilon, okay, then the mixed characteristic polynomial of these matrices, so remember, that's just the polynomial you get when you look at the expected characteristic polynomial of random vectors which have those matrices as their covariance matrices. Then the largest root of this polynomial is at most 1 plus square root epsilon the whole square. Okay, so it's a single inequality. And it's a generic bound on the largest roots of such polynomials. This is the main thing I'm going to prove today. And the main application of this, so are there any questions about the statement? Okay, the main application of this, okay, so together theorem A and theorem B allow you to control the eigenvalues of these type of random matrices with non-zero probability.
Are the roots necessarily non-negative or?
Yeah. So okay. So we proved the roots are real. The roots are non-negative because it's an average of polynomials whose roots are non-negative. So the main application is the Kadison-Singer problem, which is equivalent, which is implied by a discrepancy theoretic statement known as Weaver's conjecture. So before proving theorem B, let me just tell you how this theorem B implies Weaver's conjecture and, well, what Weaver's conjecture is. Okay. So Weaver's conjecture is a question in discrepancy theory. And if you don't know what that is, let me just tell you the most elementary question in this area, which is discrepancy of set systems. So here's sort of the first question in this area. So suppose you're given a family of subsets, n subsets of 1 through n. Well, the goal is to find some signs, epsilon 1 up to epsilon n, So you want to think of these as, you can think of these as a coloring of these of the elements of the set, or a partition into two subsets, positive and negative, such that for every one of these sets, it's as balanced as possible. So such that the maximum over these subsets of the sum of the signs inside the subset, this quantity, so this quantity is called the discrepancy, is small. Okay? So it makes sense to call it the discrepancy. You want to think of this as, you want to partition these numbers 1 through n into two sets in such a way that for each set, almost exactly half is plus and exactly half is minus. And how far you are from being exactly balanced, that's the discrepancy. Okay, so that's a type of combinatorial problem. So this is a task, right? That you give me some subsets. I need to find some signs so that for each subset something happens. You can think of these as test functions. Okay, so one question is, as a function of n, how small should you expect the discrepancy to be, right? If I give you an arbitrary set system, can you prove that you can always do, at least, this good, at least some non-trivial bound? So the first thing to do, the natural thing to try is to consider a random signing. Okay. So what happens if you pick random signs? Well, these are subsets of n, of a set of size n. They could have size about order n. If you pick random signs, inside each subset, you expect about square root n fluctuation, right? The variance is square root n. So for one subset, you should get a discrepancy of square root n, but you have n sets. So if you union bound over them, you should pick up another log factor. And so you can prove that the probability that there exists some subset with discrepancy bigger than about n log n times some constant, this probability is much less than 1. Okay. So random signing will get you discrepancy root n log n. In a sort of very simple way, you apply Chernoff bound to each set, you take a union bound, you get root n log n. Okay. So that happens with high probability, right? So with high probability, you succeed. The probability of failure is small. So the interesting thing is that you can do significantly better than this. Okay, so there's a famous theorem of Spencer, I believe 1986, which says that you can always get a discrepancy less than 6 square root n. So you can beat this randomized argument. And for any set system, there exists a coloring which gets discrepancy significantly less than this, 6 root n. I won't tell you how the proof works, but it's not a it uses some probability, but it doesn't. These good signings are rare, and Spencer's proof shows that nonetheless that they exist. Okay. And okay, I just want to mention from an algorithmic point of view, this was proven a long time ago, but it took several decades to show you can find the signing in polynomial time. Okay. So that's an introduction to one problem in discrepancy theory. Any questions about that? Okay. So Weaver's conjecture is a question you can think of as a spectral discrepancy theory. And here you're given a set of vectors. Instead of a bunch of subsets, you're given a set of vectors. And they're normalized so that the covariance matrix is the identity. So in other words, you know that summation vi transpose is equal to the identity. And concretely what this means is that for every unit vector x, the variance in the x direction of these vectors is 1. Okay, so you're given these vectors, and the goal is to again find signs, so one sign for each vector, such that, now what would you like to have happen? Well, the original vectors have the property that the variance in every direction is 1. You would like to find signs so that in every direction the variance is about evenly split between the plus and the minus vectors. So the property you want is such that for every test vector x, the summation epsilon I vi x squared, this quantity is small. So let's call this a max. So this is my definition of spectral discrepancy is small. Okay. So here you had finitely many tests, right? For every subset you had a test. Here you have infinitely many tests, right? So for every vector x on the unit sphere, you you look at the variance in that direction, and you want to choose the signs so that this is as small as possible. Okay. So the variance is evenly split among the pluses and minuses. Okay, so that's a spectral discrepancy type problem. Now, okay, so what should you be hoping for here in discrepancy, right? So, I mean, I told you that the original vectors had variance 1 in every direction, or at second moment 1 in every direction. So trivially I can get 1 over here, right? Just by setting all the signs to be 1. And in general I actually can't beat 1. Okay, so as stated, this problem does not have an interesting solution because of this example. You consider the example where you're given vectors, just a standard basis. Right? So certainly these have covariance matrix equal to the identity. But now for any signing, well, the norm is just 1, right? Because this is a diagonal matrix with signs on the diagonal. So certainly, I mean, okay, this quantity is just a norm. Maybe I should write it this way. Right? So the norm, so for this example, you can't beat 1. There's no non-trivial, there's nothing you can do. So to make this a sensible question, you have to add one more condition, which is the vectors are not too long. Okay, so if any of the vectors are unit vectors, you're going to run into this problem. It doesn't matter what sign you put, you're going to get a normal 1. So Weaver's conjecture is, let's say you now throw in the condition that the vectors are short, bounded by some constant delta, okay, which is less than 1.
It means that there are kind of many of them, right?
Yeah, so you're right. If delta is small, it means that there are at least n over delta vectors, just by computing traces. Okay. So the vectors being short also implies that there are many of them. Okay, so this is a problem which is parameterized by delta, and for every delta, there should be some best discrepancy you can get. And Weaver's conjecture is that there exists some universal constant delta such that the discrepancy you can get for that delta is strictly less than 1. Okay. So if you ask that the vectors are sufficiently short, you can always find the signing that gets you a non-trivial discrepancy that's bounded away from 1. That's Weaver's conjecture. Okay. Now, again, for this problem, you can try a random signing. Now, originally in the combinatorial setting, we used a Chernoff bound to analyze a random signing. Here, this is a random matrix, but there are tools for analyzing norm of random matrix like this called the matrix Chernoff bound. And so matrix Chernoff implies that the norm of this random matrix is always bounded by square root delta log n. Okay, so again, if you're willing to somehow pick up this extra log factor, you can solve this problem using standard probabilistic techniques. Okay, so it's fairly easy to prove that if you're given vectors, so this bound is meaningless unless delta is less than 1 over log n. If you're given vectors whose norm is going to 0 as n goes to infinity, like 1 over log n, then indeed a random signing will solve this problem. Okay. The Weaver's conjecture really is that there's a constant independent of the dimension. So, I mean, the reason this is so important is that this is actually the statement. If you transform it in some way and take some appropriate limit, you get a solution to some function analysis problem called the Kadison-Singer problem. And for that, it's very important that the bound you get doesn't depend on the dimension. But even from a discrepancy theoretic point of view, we're seeing the same phenomenon here, that random gets you some solution with a log factor. Can you remove the log factor?
It becomes some infinite dimensional statement, right?
Yeah, it can become an infinite dimensional statement if there's no n. Yeah. Okay. So, the theorem that we prove, or that we proved quite a long time ago, is that for any delta less than a quarter, the discrepancy is actually less than order root delta. Or I mean, I guess if you allow order, you don't even need that. Just the discrepancy is order root delta. Okay. So if you choose constant length vectors, you can always solve this problem with constant discrepancy. And so that solves this problem. Now let me quickly tell you, so are there any questions about the statement of the theorem? Okay. Let me now just tell you how this is, how it's sort of an immediate consequence of theorem B. Well, or maybe before telling you the proof, let me explain to you why this problem is sort of tricky. So let me show you the two extreme examples that any proof of this conjecture has to handle. So the first example is, let's say I give you vectors that look like this. So I take the standard basis. Those vectors have norm 1, but let's chop it into vectors which have squared norm delta. Okay, so let's make 1 over delta copies of square root delta times the standard basis in each direction. Okay, so this is a particular instance of this discrepancy problem. Okay. So Weaver's problem for this set of vectors asks, well, I want to put pluses and minuses on these vectors so that the norm of the resulting matrix is small. I mean, this is very easy. This is just the matrix. I'm sorry, not EIs. The matrix that you would get in this case is just a diagonal matrix. It's very easy to control its norm, and the appropriate coloring is just make half plus and half minus in every direction. You actually get 0 if you have even number of vectors if you do that. Okay. So in this example, the very simple greedy algorithm, I'll call it, works, but random fails. Okay, so if you have a constant number of these vectors, if you do it randomly, you're going to get all pluses in some direction. So this is the hard example for the matrix Chernoff bound. This is the example where a random signing fails. On the other hand, there's a very different type of example where the vectors are just random. And on this example, it's easy to prove that random works using some random matrix theory. And greedy, I have no idea how to analyze it, right? If you give me a bunch of random vectors and you try to find some deterministic algorithm that partitions them into, almost these balanced sets, I don't know how to do it. Okay, so this is somehow the difficulty of the problem. So now we'll see that theorem B just doesn't even notice this and just immediately solves this problem. But the point of these examples is to show that any solution must be somehow with low probability. So now proof of this theorem. Okay, so we're given these vectors. So given v1 through vm, these are in Rn. Consider the following random vectors. Let's make a random vector Ri for each vi that's just equal to vi0 or 0 vi times square root 2 with probability half each independently. Okay. So you gave me this discrepancy problem. I constructed a bunch of independent random vectors that do something very natural. They either embed this vector in a top block or a smaller block of some vectors in 2n-dimensional space. Okay. So now you have a random matrix, right, of the type that theorems A and B talk about. So what does this random matrix look like? Well, it's a block matrix. So there are these two. So there's a 2 in the front. The top block contains all the vectors that received, I don't know, let's call this a plus sign. So let's call this T1. And the bottom block contains all the vectors that received the minus sign. That's the random matrix, right? Just multiply by 2 and put half of them in this block, half of them in this block. But now the norm of this matrix is just the norm of this matrix, and this is a block matrix, so this is twice the max over J of the norms of these blocks, right? Okay. So it's a random matrix whose norm controls the norm of, the maximum of the norms of the pluses and the minuses. Okay. Now what does theorems A plus B, what do they tell us? They tell us that with non-zero probability, this norm, which is the largest eigenvalue of this semi-definite, positive semi-definite matrix, this is at most a 1 plus square root epsilon squared, where what's epsilon? Epsilon is the maximum trace of any of these covariance matrices. And these are easy to compute, right? Because these vectors are, they have squared norm at most delta. So each of these covariance matrices will have trace at most 2 delta. Okay. So theorem A tells you can compare this to the expected characteristic polynomial. Theorem B tells you the expected characteristic polynomial has roots bounded by this quantity. Okay, theorem B also had an additional condition which you have to verify, which is that the sum of the covariance matrices is the identity. And that's easy to verify, right? So if you look at the expectation of this matrix, you'll just get twice times identity over 2, which is the identity. Okay, so these were the conditions of theorem B. I verified them. Theorem B implies this bound on the norm. This is 1 plus square root 2 delta squared. Now why is this good? Well, this is good because this means that if I look at the sum of the vectors in each of these sets, the norm of this is half the norm of this big matrix. So the norm for one of these sets will be 1 plus square root 2 delta squared over 2, which is half plus whole square of delta times identity. But now this is actually true for both the set and its complement. Remember, because I've partitioned my vectors, which add up to the identity, into two sets. And so what that means is, well, if the eigenvalues of this are upper bounded and the eigenvalues of the complement are upper bounded, complement with like identity minus the matrix upper bounded, I also get a lower bound. Root delta. Okay? And so now, if I just take the difference, I get the bound that I wanted. So if I look at the sum inside T1 minus the sum inside T2, so it's an immediate consequence of this theorem A and B, which gives you a dimension-free bound on the norm of a random matrix of this type. Okay, so any questions about that? Okay. Okay, so now I'll just spend the rest of the time explaining the proof of theorem B. So theorem B is a statement that if you give me a bunch of matrices, positive semi-definite, adding up to the identity, and with bounded trace, epsilon, then the mixed characteristic polynomial has a bounded root. Right, so largest root of the mixed characteristic polynomial is at most 1 plus square root epsilon. Okay, so the strategy relies on an exercise from yesterday, which some people did. So this polynomial we observed, this is a univariate polynomial, we observed it's a restriction of a certain multivariate polynomial. So we derived a formula for this polynomial. It was 1 minus product of 1 plus partial zi determinant of xi minus sum of So our goal is to control the zeros of a polynomial like this. Right? Okay. So it's going to be slightly more convenient to rewrite this again by doing a simple change of variables. So I'm going to replace z with minus z. That'll flip these signs. And I'll use the fact that summation of ziai, summation xai is just equal to x times identity. Right? So I've assumed the vectors add up, the rank 1 matrices add up to the identity. So if I use this fact and do a little change of variables, this polynomial is actually equal to product of 1 minus partial I. So I'm going to write partial I for partial zi of determinant summation zi ai when you restrict all the variables to be just equal to x. Okay. So my goal is to show that under these analytic assumptions on the matrices AI, I can bound the roots of that polynomial by 1 plus squared epsilon squared. Right? Okay. So this polynomial, well, it consists of a determinant, sort of relatively simple determinantal polynomial like this, whose zeros I can actually understand, right? So I can think of this problem as simple. Why? Well, so let's call this polynomial Q naught. Okay, so I can easily identify a large zero-free region for Q naught and get an upper bound on the zeros of its restriction along X. Why? Well, observe that the set K naught, which is the set of all Z in Rn, so that summation Zi Ai is positive definite. Okay, so this is a section of a positive semi-definite cone. This is a zero-free region for Q naught. Right? I mean, if this matrix is positive definite, this polynomial is not zero, and so its restriction is not zero either. Okay. So it's easy to understand zero-free regions for this polynomial. The whole game is, well, what happens to this cone? What happens to the zero-free region when you apply these differential operators? Okay, so strategy is to understand perturbation of zeros, or perturbation of zero-free regions under these differential operators. Okay, so that's what I'm now going to explain how to do. Okay, so rather than diving straight into this, that how do you understand the zeros, perturbation of zeros of these multivariate polynomials, I'm first going to show you how to understand perturbation of univariate polynomials. So you can think of this as a warm-up for the actual task of controlling the zeros of this polynomial. So let's suppose I have a real-rooted polynomial p of x. And let's say I now subtract off its derivative. Okay, so that's the kind of thing I'm interested in doing. So I'm going to use this partial notation because it's going to be sort of pedagogically nice later. So 1 minus partial p is actually just p minus p prime. And in general, if you actually care about this, if you look at the largest root and you subtract the derivative, it can move around a lot. It can, you can't prove good worst case bounds on it because, for example, consider this polynomial. Consider x to the n minus its derivative. Well, that's x to the n minus n x n to the minus 1. That has a 0 at n. So just by subtracting the derivative once, you increase the largest root by n. Okay, so it doesn't really make sense to prove worst case bounds on the largest 0. It's very unstable if the largest 0 has high multiplicity. Okay, so maybe the point of this is that zeros can be unstable. And so the idea is, well, instead of looking at the zeros, you look at some smoother quantity, which can upper bound the zeros. Okay, so the key object in controlling zeros under these types of perturbations is the following rational function that I'm going to call the barrier function, although it's like a hundreds of years old object. So phi p of x is a rational function that's going to be derivative of p divided by p. Okay, let's assume the polynomial is monic.
So are we still in the univariate case?
Yeah, this is all in the univariate case. I'll tell you when I'm switching to the multivariate case. Okay. So what is this? Well, it's a rational function whose poles are just the zeros of the polynomial. Okay. So let's say it has zeros lambda 1 through lambda n. Okay. And okay, I mean this is also just a derivative of log p. Right. Okay, so what does this look like? Well, it's a rational function, as I mentioned, whose poles are at the zeros. So if the zeros look like this, then this is a rational function that looks like this. And one obvious thing is that the zeros of p correspond to the poles of the barrier function. That's obvious. The interesting thing from the point of view of these differential operators is that this barrier function actually also tells you the zeros of p minus its derivative. Why? Well, let's say you look at the level set where the barrier function, which is just by p equals 1. So let's say you look at the set of points, which are not poles, but the set of points where the barrier function is equal to 1. Well, if derivative of p divided by p equals 1, if you rearrange this, this just means p minus its derivative is equal to 0, right? So actually, this rational function encodes the locations of zeros of p minus all multiples of its derivatives, just by looking at these level sets. So, so zeros of p minus its derivative correspond to points where this barrier function is equal to 1, as opposed to infinity. Okay? And in fact, you can use this observation to prove upper bounds on the locations of the zeros by studying. You don't need to find a point where it's exactly equal to 1, by just finding a point where the barrier function is sufficiently small. So here's the observation. So if you have some number that's bigger than the largest root of a real rooted polynomial p, and you know that the barrier function of p at this point is strictly less than 1, then actually this point has to be bigger than the largest root of p minus the derivative of p. Okay, what's the proof of this observation? Well, let me erase this. The proof of this observation is we observe the largest root of, so this is the largest root of p. Maybe I'll use a different color. Okay. This is the largest root of p minus its derivative. Well, the key point is that this function is monotone decreasing above the largest root of p. That's sort of easy to check. So once you're above the largest root of p, this is a monotone decreasing function. So that means if you found some other point, let's say some point b here, where the value of the barrier function is less than 1, it has to be bigger than the largest root of p minus its derivative. It's a very elementary observation. Okay. So if you can find such a point, that gives you an upper bound on p minus the derivative of p. Okay, so that's how you understand perturbation of the roots of a polynomial under one of these operators. Any questions on that? Okay. But now this isn't really good enough, because what about, what if I did this a bunch of times? Right? My actual polynomial I'm interested in, I mean, if this is in any way related to that, involves applying a whole bunch of these operators. This argument is not going to get me very far, right? So I start off with p. Okay, I somehow calculate its barrier function. I find a point where it's less than 1 that gives me an upper bound on the largest root of this perturbation. But then what do I do, right? I mean, I can't apply this inductively because I don't know anything about the barrier function of this polynomial. So ideally what I need is a robust version of this which relates the barrier function of the polynomial to the barrier function of the perturbation, and then I can induct. So this is a robust version of this lemma. And here's what it says. So this was proven in a paper with Batson and Spielman essentially in 2008. And what this says is the following. So if p of x is real rooted, and you have a point that's above the largest root of p, and not only is it above the largest root of p, you have some control on the barrier function at this point. And now you have something better than 1. So here the observation you just said if the barrier function is less than 1, that gives you an upper bound. Here I'm asking the barrier function is less than 1 minus 1 over delta. So delta is some number that's positive number that's bigger than 1. Then b plus delta is bigger than the largest root of p minus its derivative. And you get the same, you actually get control on the barrier function of the new polynomial at this point. Phi of p minus its derivative at b plus delta is less than phi of p at p. Okay, so okay, maybe this is a bit, this is a lot to handle, but the way to conceptualize it is this point, a point b which satisfies this property, a point that's above the roots of a polynomial and the barrier function is bounded, I'm thinking of that as a delta robust upper bound. Okay, so instead of looking at just upper bounds on the roots, I'm going to look at upper bounds where this function is small. And intuitively, those are points that are actually stable under these perturbations. Okay, they vary in a smooth way. What the theorem is saying is exactly that. If you find a delta robust upper bound, then b plus delta is a delta robust upper bound for p minus its derivative.
Is it 1 minus delta or 1 minus 1 over delta?
I'm sorry, 1 minus partial, no, this is 1 minus 1 over delta, sorry. 1 minus 1 over delta. Oh, okay, so you're asking what's the intuition?
You recover that for delta equal to 0.
Delta is bigger than 1.
No, you recover this for delta equals infinity, right? So in this case, all you know is it's less than 1. So delta could be huge, right? That makes sense because think about this example. So here, okay, wait. Let me think about this. I'm sorry. This statement is for any delta bigger than 1. I mean, okay, for delta less than 1, this is negative. For any delta bigger than 1, right? If this is less than 1, you get this for free. And this statement doesn't say anything about the barrier function. So.
But the second one then doesn't say anything. The phi plus delta for large.
This?
No, the one above.
This.
Yeah. For large delta doesn't say anything.
But you can.
Well. Okay, so.
I think think it's fine. If delta is large, then you cannot say anything.
Yeah, okay. So I think the point is the conclusion here is stronger, right? So the point is I'm taking this whole thing as a conclusion, and you're right, this does not recover this, because here the conclusion is weaker. I'm not asking anything for the barrier function here, only for being larger than the largest root. You're right, if you take delta to infinity, you don't get anything here, but that's not because of this part, it's because of this part. Does that make sense? Okay, another way of putting this is, this has a stronger hypothesis and a stronger conclusion. It's not a generalization of this statement above. Is that right? This is a stronger hypothesis. This is a stronger conclusion. Okay, so this is a delta robust upper bound on P, and this is a delta robust upper bound on P minus its derivative. And now this is good because you can induct. Right? If you have a lemma like this, you can start with some polynomial. You can start with a delta robust upper bound on its roots for some appropriately chosen value of delta. So let's say this is your B1, and you know that phi of P is less than some value that you'll set. So 1 minus 1 over delta. And now the point is that when you apply this differential operator, this will move by delta to get some value B2, and you'll have exactly the same induction hypothesis here, that phi of P minus partial P is less than 1 minus 1 over delta, and you can continue doing this any number of times. Every time you just move by delta. What this is trying to articulate is, if instead of looking at the roots, you look at these particular level sets of this function, they move smoothly.
I'm just confused. So the first conclusion, B plus delta is greater than lambda 1. Don't we already know from above that?
Yeah, so this is weaker than this, yeah. So that's exactly Pablo's question, right? So, I mean, this is just because, this doesn't, I mean,
okay.
I need this as part of the assumption. If you're working inside the eigenvalue somewhere, none of this makes any sense, right? Because it could be negative and stuff like that.
It's correct, but just...
No, I'm just trying to, yeah. Any other questions?
So the proof doesn't have any hidden tricks, or
The proof doesn't have any hidden tricks, so let me show you the proof. So I can, let me show you the proof on this slide, on this board. Okay, keep swapping these. So what's the proof? Well, okay, so I have some polynomial P, and I have some point above its roots, and I know something about its barrier function. I want to know something about the barrier function of polynomial minus its derivative at a point that's now a little bit bigger. My goal is to prove mainly this inequality, then this follows easily from some continuity argument. Okay. Okay, so let's just write down what this is. Well, the first thing to observe is, so observe that P minus its derivative is just P times 1 minus its barrier function. That's just from the definition. Okay, so what that means is that this new barrier function is the derivative of P minus its derivative, which is P times 1 minus phi of P, divided by P times 1 minus phi of P. Evaluated at this point, B plus. Okay, that's just the definition. Now, if I just differentiate this, I get two terms. So in the first term, the p's cancel, and I get a minus the derivative of the barrier function, 1 minus the value of the barrier function. In the second term, I get derivative of p over p, which is just the barrier function itself, again evaluated at the point b plus delta. Okay. And what I want is I want this to be less than the barrier function of the original polynomial at the point p. Okay. So now and I'm going to make two observations, which I guess I erased them, but they follow from the picture of the rational function. So let me write them here. So one is that this function is monotone, decreasing above the roots of the polynomial. So phi p, p minus p plus delta is greater than or equal to 0. So this is monotonicity. Okay, and this follows from this picture, right? Here it's monotone decreasing. Here, suppose you were at b over here. If you go to b plus delta, you get something strictly smaller. Okay. What that means is that well, this quantity is just phi of p. What that means is if I rearrange this inequality, this means I can rearrange this inequality to get so all I did is I moved this to the other side and took it under the denominator and moved this up. And the reason I could do that is it's a non-negative number. Okay.
We still want to prove it, right?
We still want to prove it, yeah. So we want, okay, so this is the statement we want. And I'm claiming that the statement we want is implied by this statement.
So it's stronger.
It's stronger. Well, it's actually equivalent. Okay. And I use monotonicity here because I needed positivity of the denominator to rearrange it in this way. Okay. Now, I'm going to use one more property. So I'm going to use monotonicity again to say, well, a stronger statement would be to replace this by a smaller number. So I can replace this by 1 minus phi p of p. Or maybe I'll put the arrow here. And now I'm going to use one more property, which is convexity. So this function is also convex above the largest root. It's not just monotone, it's also convex. That means that if I care about this difference, which is what appears in the denominator here, it's going to be at most what I would get if I took the linear approximation with this tangent. In particular, this inequality is implied by an inequality I get if I replace this by a smaller quantity, which is the linear approximation. So this is implied by the inequality minus the same thing, but now I replace this with the linear approximation. What is the linear approximation? Well, it says that the value of the barrier function at b minus the value of the barrier function at b plus delta. This is at least delta times minus the derivative. That means I can now replace this by delta times minus, I'm sorry, these are all in B plus delta. Okay, but now these cancel. You get 1 over delta less than 1 minus the potential, which is the assumption in the theorem. Okay, so I guess I shouldn't have erased the statement of the theorem, but the assumption in the theorem was that the potential is less than 1 minus 1 over delta. This is the assumption. Okay, so that's the entire proof. It's just these 4 lines. Now the reason I showed you this is not because I want to do some annoying calculations, it's because I want to show you that the proof of the multivariate thing is almost the same. So any questions about this before I move to the multivariate case? Okay. So multivariate perturbation. In the multivariate case, I have a real stable polynomial. And I don't have roots, right? I have some variety of zeros. I have some zeros that are not discrete. So what I'm going to be interested in as an upper bound on the root is the following set. It's going to be the set of points such that when you look at the polynomial and you look at an orthant with a corner at that point, then the polynomial is non-zero. So the picture is something like, I have a polynomial like this, it has some zeros, I'm interested in Kp is the set of all points x, so that when you look at this orthant, the polynomial is non-zero. That's my notion of an upper bound on the roots. So now I'm going to be interested in tracking the movement of these sets as I apply differential operators. Okay, so let me continue writing here. Okay, so I want to keep all this. So that's my notion of upper bound, and I'm going to have a notion of barrier function. So this is going to be, again, a rational function given a real stable polynomial. The barrier function in the ith coordinate at a point z is partial I p over p evaluated at z. So z is now a vector, right? I'm going to define this for I goes from 1 to m. Okay, so there are two there are two lemmas about this. So lemma 1 is that this function, so this is some rational function that's defined in Rn. But if I look at what it does inside this cone, it's going to have very nice analytic properties. Okay, that's what allows this proof to go through. The first lemma is if I look at these multivariate barrier functions, at any point, maybe I'll write it like this. So if you have a point that's above the roots of a real stable polynomial, then if you look at the function, if you look at the barrier function, any of these barrier functions, in a direction, in any of the coordinate directions, so this is a univariate function, is monotone and convex. Okay. So if you look inside this cone, these barrier functions are literally what you get if you restrict all the variables and look at the barrier function along one direction. The claim is that these are monotone and convex. Sorry, this is important. But not just in the direction that the barrier function is defined in, but in all the coordinate directions. Okay? And using this, you can prove lemma 2, which is a word almost verbatim. It's almost the same as the lemma I proved earlier in the univariate case, and it's the following. If you have a point that's above the roots of a multivariate polynomial, I'm sorry, if P is stable, B is above the roots, and these multivariate barrier functions are bounded by 1 minus 1 over delta, then B plus delta, no, let's make this J. Then B plus delta Ej. So this is all about what happens when I perturb the polynomial with a differential operator 1 minus partial j. This is above the roots of P minus partial JP. Okay, so that's the point. I can relate the cone for P to the cone for P minus partial JP. And none of these potentials blow up. So phi sub I, P, B plus delta Ej less than phi I, EP for all I. Okay. So it's syntactically almost identical to what I wrote in the univariate case, except the picture is different. So I've replaced just a usual derivative by a partial derivative, and now I have to move this upper bound in space. It's not just a number. I don't just move it up. Yes.
One of the indices should be the P minus delta JP, partial JP.
Oh, I'm sorry. P minus partial JP. Yeah. Okay. So the picture associated with this is, I had my real stable polynomial. I had some upper bound B, and now once I subtract the derivative in direction j, I have to move this up, B plus delta Ej. And the claim is that if I do that, none of these potential functions increase.
In lemma 1, can you replace Ej by any positive vector?
You can, but I'm just stating it this way. You can replace Ej by any positive vector. So it's actually convex in the whole orthant, monotone convex in the whole orthant. Okay, so now the proof of lemma 2 is pretty much already in the board. Let me just show you that the same proof works, assuming lemma 1, assuming monotonicity and convexity. Okay, so what's the proof? Proof of lemma 2. Well, okay, this still works, right? If I subtract off the jth partial, it's like multiplying by the jth barrier function. Okay, so now I'm interested in the ith barrier function of the polynomial perturbed in the jth direction. Okay, for the induction to work, I need to control all of the barrier functions. That's the subtlety. And now I'm interested in it at the but now I'm moving my barrier in the j direction up, as shown in that picture. Okay, so let's just follow our nose, right? So you get a partial I, because this is a barrier function direction I. The perturbation is in direction j, so you get j's here. And this is Ej. And now here, this works the same way. You get partial I of the jth barrier function. This is still a j. Here you get the ith partial, sorry. This is again Ej. And you want this to be less than the ith barrier function of P at B. Okay. So this is exactly, I'm just writing out the new barrier function of the perturbed polynomial at the new point and relating it to the barrier function of the original polynomial at the original point. So again, by lemma 1, I have monotonicity of the ith barrier function in the j direction. Right? So I have that. This is still true. So I can still do this rearrangement, and I will get the same thing. Okay. So this j goes to the other side. Okay. And now to do the final cancellation, I need convexity, but I also have that, right? So I have convexity of the ith barrier function in the j direction. So now I'll get a partial I phi j. Okay, but now something funny happens. Here I get a partial j phi I, right? Partial j phi I, because I'm moving in the j direction. In the denominator, I get a partial j phi I. In the numerator, I have a partial I phi j. Otherwise, everything else is the same. Okay, but partial I phi j is partial I partial j log b. And partial derivatives commute. So it's actually the same as partial j phi I. This is the one sort of one minor difference in the proof, but then you cancel these and the same proof works. Okay, so it's the same proof. It's a like 5-line proof. The main ingredient is establishing monotonicity, this monotonicity and convexity, which I won't have time to explain how it's done, so I'll just state what tools are used. But are there any questions before that?
Right, so when you replace this function by affine, right, so it's never sharp, but it's becoming sharp when the roots go to infinity, is that right? Or?
Wait, what's never sharp? Oh, you mean this?
Yes.
Yeah, this is, okay, so here as stated, this can never be sharp, right? Because if I actually wanted b to be at a root, this would have to be infinity, right?
Okay.
And I'm insisting that delta is bigger than 1, so
It's
this,
sort of becoming sharp, right, as the root goes to infinity, probably, right?
which inequality is becoming sharp?
The convexity.
Oh, the convexity, oh yeah, sure. The convexity inequality is becoming sharp as the root goes to infinity. The function is becoming linear. That's right. Okay. Anyway, I guess that's, I mean, I think I'm already considerably over time, so let me just, so the key thing is to prove lemma 1, which is monotonicity and convexity, and then the univariate proof works. And so monotonicity and convexity follow from two theorems that I think will be discussed in the work. There are two options. One is the Helton-Vinnikov theorem, which says that bivariate restrictions of real stable polynomials are determinants. And the second is convexity properties of the function log p in the set Kp, which is actually the hyperbolicity cone of the polynomial p, and this follows from results in hyperbolic optimization. Okay, but I guess I don't have time to talk about it. But the only new thing you need is these monotonicity and convexity statements. That's how
You can use either, right?
you can use either, yeah, or. Okay, and I guess that's it. Any questions? Okay, so how much time do we have total?
Do you want to go? We can resume at 10:45.
Yeah, maybe we take a 5-minute break. Yep.
Yeah, 5 minutes.
We have an open problem thing too, right?
Yeah.
Yeah.
We can
Yeah.
try it for 10 minutes.